This is OPI Structure Part 2, Table Calculations.
Let's put these all together in a realistic example using index match and SUMIF with structured keys. This is a segment of a BOM file, Bill of Materials, describing the structure of items to be used in a project. There'll be a later training module on this channel about BOMs. The field called element, together with field element rev, lists items used in a foreign allocation table to allocate items for use by organizations. In this example, you might allocate racks or storage appliances or dev rack systems, the items listed in the element field. An element is typically built from several subassemblies that have to be built or bought. This BOM file is used to explode elements into their comprising subassemblies to be acquired in order to deliver an element that's allocated. So in this table, each element is broken into several records, one record for each subassembly that needs to be built in order to supply the element. The needed subassemblies are specified in fields subassembly and subassembly rev. Several fields further describe how we'll acquire each subassembly. The field subquantity says how many of each subassembly are needed to construct each element. The field subbuildBy says whether we'll build or buy the subassembly. The field subcost states the cost of a single subassembly item, and the field xcost states the extended cost of the number of subassembly items needed as specified in the field subquantity. So each element is broken down into several records, one for each subassembly needed for the element. Each record then describes one of the subassemblies, including subquantity needed, whether to build it or buy it, and lists the cost of the needed subassembly and the total cost of the needed quantity of that subassembly for that element. The foreign table allocation, listing elements allocated to organizations for use, is joined by the database tool with this table, and that join explodes a single allocation record into several records in the query result, resulting in a list of subassembly items to be built. We'll cover joins a little later in this module. For this example, let's examine how the field subcost, the cost of a single item of a subassembly, is calculated. The subassembly itself may be a buy item, which is specified here in the subbuildBy field, in which case we'll look up its cost from a record in a foreign table containing item data. If subbuildBy specifies that it's a build item, that subassembly will also be listed in this BOM table as an element to be built, further breaking it down into more subassemblies needed to build that subassembly. So to find the cost of a subassembly, we'll have expressions that walk down the BOM table down to items that are buy items where we can look up the cost. If it's a build item, the subcost expression for that subassembly will add up the extended cost of all the subassemblies to build itself. Line 65 is the first of several lines, 65, 66, and 67, listing subassemblies in column subassembly, comprising a dev rack deliverable element that may be allocated. Line 65 says that a dev rack rev P2A contains a subassembly called storage appliance rev P2A. Line 66 and 67 specify other kinds of subassemblies needed as well for a dev rack P2A. The question to be answered is, what's the cost of that storage appliance P2A assembly? The quick answer preview, the subassembly calculates its own cost by adding up the cost of all items needed to build itself. Now, how is that done? The BOM table has all the information we need without needing a database join, so let's do that. Each element record contains two structured key fields. One key in each record identifies the element in that record, BOM item key in. The second key identifies a subassembly also in that record, BOM item key out. Each of those keys is a structured key concatenating the element name with its element rev, or the subassembly name with its subassembly rev. Now look at the BOM tree structure created. The BOM item key out for the storage appliance P2A subassembly on line 65 matches the BOM item key in records, defining items needed to build a storage appliance P2A element. And that storage appliance P2A element is defined itself by 3 records listing subassemblies needed to create itself. Each of those items has a field stating its extended cost. That's just what we need. This is just the information we need to put together a SUMIF to add up the extended costs of all items needed to build the item. So look at the expression in the center of the page. That's the expression determining the subcost field in each record, stating the cost of 1 unit of the subassembly specified in that record. That subcost expression first determines if its subassembly is a buy item. If it is a buy item, it'll look up the cost of the subassembly from a foreign table. For now, we're going to ignore that. If the subassembly is a build item, the SUMIF will be calculated. That SUMIF searches the BOM table BOM item key in field for element records matching the key BOM item key out for the subassembly to be built, and sums up the extended cost of all element records matching that key. In other words, it adds up the cost of all subassemblies needed to build the subassembly listed in this record as needed to build the element listed in this record. And that's the value of subcost for the storage appliance P2A in record 65. Then the field XCost multiplies that subcost by the subquantity field of the record, and that's the total cost for that subassembly needed for 1 unit of the element. This provides a calculation structure in the BOM table that walks down the assembly tree structure for each element until the purchase cost of items needed to be built can be looked up and adding up all those costs. This is a complex example, but I wanted to show you the power of these functions. If you're confused by the structure, just focus on the SUMIF for now and see how it adds up the values of the required items. It doesn't have to know it's part of a larger structure. There'll be a later module going into BOM structure some more. Also notice the index match structure in part of the expression that we ignored. It's used to look up a single cost field value from a foreign table called table elements, the cost of purchase if it's a buy item. Now another example with a little simpler structure. This is a piece of an allocation table used to allocate equipment for organizations to use. The equipment is grouped to show a rack that will contain it, and then the elements are listed with the quantity of each element and field quantity element, the type of equipment and class element, we used index match to get this from the table element data shown, and the slots available in each element in slots total. There would probably be more records too in a complete allocation table. Each record has several structured keys. The first key, item ID key, is the identifying name of the element without a rev that will be used to link in non-rev specific element data. You can also see table element data peeking out, the foreign table containing the non-rev specific element data. The second key, RNIC key, is constructed to identify element type specific to each rack. There would also be an additional rev-specific structured key that I didn't show, containing the element name in rev, used for explosion and to pick up other element rev-specific data. Of course, the table was constructed to hold data on equipment allocation, but we also added structure to it to solve a particular problem. The problem to be solved is, how many RNICs should be allocated to each rack? The way to solve this problem is shown in the outlined box at lower right, working backward from the desired result up to the number of RNICs to be in the quantity element field. So working up from the bottom of that box, first will be dependent on the number of servers allocated to each rack, in particular to the number of slots in each server type. Second, we'll want to identify server records for each rack, and third, we'll want to sum those server records for each rack. So first we figure out the slots total for each record containing servers. That'll be the quantity of servers on that line times the slots element entry in table element data. It's a single value, so we use index match to go get it from table element data. Just in case there's no entry, or if anything else fails, we wrap the entire index match construction inside an if error, returning quantity 0 on failure. We often wrap lookup functions. The index match looks up slots element from table element data. It indexes into table element data. The first match uses the item ID key from table alloc to find a match in the element ID key field in table element data. If there's a match, it returns its row number within the table element data. If no match, it returns an NA error. The second match finds the column slots element in the header row of table element data. If there is one, it returns its column number within table element data. If not, again, an NA error. Index then finds the cell in table element data at the row and column as specified and returns its value. If a match returns an error, the if error jumps in and returns a 0 value. The value returned by the if-error index match is multiplied by the quantity element field in table alloc, a number entered by you when defining the configuration, and that result is the slots total shown for each server record. Back to the lower right box, we're going to want to sum the number of server slots in each rack name to be able to say how many RNICs are allocated to that rack name. So we have to be able to identify servers in each rack. There might be several server records in each rack name, maybe several servers for web, application, database, and a management server. So we construct an RNIC key to identify records that state class element value as server in a rack name. That makes an RNIC key value for every item in table alloc. The ones we want to sum slots for all have RNIC key value containing their rack name concatenated with the string server. Now we can create an expression for the quantity of RNICs allocated in each rack name. Since there may be several server records for a rack name, we use SUMIF. We're looking in the same table, so we don't have to specify a foreign table name in the SUMIF field name parameters. The RNIC records each specify the rack name in which they are installed. So in each RNIC record, the SUMIF for the value of quantity element specifies the lookup key as bracket at rack name close bracket, and concatenates a colon character and the string server that will match all server records with the same rack name as the RNICs. We specify slots total as the field to sum, since it contains the aggregate number of slots for servers in each record that will match. And that sums up the total slots among all servers in the rack containing those RNICs. When creating keys for database joins, most joins use a pretty straightforward common set of key values. You can see the construction and example values of those keys. The item ID key identifies an item containing or seeking non-rev specific data. The item rev key adds the element rev and is used to connect to rev specific data, information specific to a particular build named by the rev. The item task key adds a specific task ID, meaning task name, looking for data on a specific task. This is usually task dates, and these keys are constructed within the Microsoft Project Gantt plan. There's a training module showing how to construct the Gantt and construct it via these keys into Excel and to the database. Keys constructed for Excel table lookups, as in the previous two examples, tend to be more application-specific and more complicated to tightly specify records needed for particular use. The two preceding examples, though, pretty much show the thinking and implementation for that type of key.
This OPI structure sequence continues in OPI structure part 3, architecture implementation.